Okay, so good afternoon, and thank you all for being here. I'd like to thank everyone associated with this conference, from the visionaries, the organizers, and all the participants. It's really humbling for me to be here because I have participated in several of these conferences, and I so respect the men for who this conference is named. And it was really tough for me to choose something to talk about. And in the end, my abstract is very general. And I'm hoping that it will appeal to all of you because it's more about prediction. And the question is, are you doing predictions well? Okay. So just a couple talks ago, we heard Du Bois mention prediction regarding Parkinson's disease, and Stan before mentioned prediction with respect to compounds. Are they going to be active in response to some biological assay? But prediction is very, very broad. Whenever we think about applying for a loan at a bank, we provide the bank with lots of information, and they do their work, and they run that data that we provide to them through their model to try to predict if we are going to be able to actually pay off our loan. And those people with high scores are considered for getting a loan. Not everyone is going to be offered a loan, even if they are deemed worthy, because the bank has limited resources. And so the bank will be ranking each individual according to what they believe is their estimated probability of repaying the loan. Another example may be you submitting a query to Google. You provide keywords, and Google returns results. Okay? They return results in a way that is ordered according to what they hope is relevance for you. And you're hoping that if you select the first 5, you're going to find something that is indeed what you want as an answer. Okay? So the goal here, and my focus, is that you are interested in prediction from the point of view of being able to identify individuals or subjects that have some sort of quality of interest. And you would like to assess the prediction model, whatever route that model was developed via, you want to assess whether that model is effective. Okay? And today, my work is motivated by drug discovery, but that's not, I don't want you to be limited by that. And so the first part of the talk, Stan already went through that. I'm going to skip by that. I want you to think more broadly. And I'm going to be talking about precision and recall as alternatives to something that's more familiar. So by a show of hands, how many people have heard of the ROC curve, or the receiver operating characteristic curve? And it is a trick question. Okay, it's a trick question because Du Bois had some in his talk. Okay, so this is the standard. And I should back up and say that I am interested in prediction or classification into several classes. Okay, so I'm not interested necessarily in predicting a continuous measure. What I want is a continuous measure. Okay, and I will then apply some sort of threshold in order to get me into these classes. All right, and the receiver operating characteristic curve is the standard, and it is the standard for a great reason. My goal is to introduce to you other curves and convince you that there are times when these should be your go-to assessment measure, and also to encourage you to be a bit cautious. So I'm going to go through the properties of these curves. I'll apply it to a data set from drug discovery, and then I'll talk about some measures of effectiveness of inference from these curves. Okay, these are the slides I'm just going to skip by, and I'm going to take you here. So the notation here is that we are learning some model. This F hat will be our learned model, whatever you want to call it. Our predictors will come in the form of the X's. Okay, so this is the input that you will be providing, whatever format that is. And there are Y's, our response values, that are unknown, and this is what we want, okay? So our prediction model will take this F hat, apply it to the input, and maybe there is some function applied to this prediction score to give us a Y hat. So here's a demonstration. The F hat function is here, and if I want really class variables, I can apply thresholds that will cut this function at various points, okay? The question then becomes, well, how do you choose these thresholds? And that's something that I'll mention in a little bit. But I want you to be thinking more broadly about this continuous measure. I don't want you to think immediately that we're getting a prediction of 1 or 0, or has the category or has the classification or not. Okay, but I am, for the rest of the talk, going to be focused on binary prediction. Okay? And if there are any questions for clarification purposes, I'm happy to take those. Yes?
Can you just say in one sentence what you mean by the G?
The G, for example, that this G right here, in this scenario, this G would be the thresholds and the step function that is created. Yeah, yeah. And it might be some other function that, yeah. Okay, all right, great. Okay, so just in terms of notation, I am now going to limit myself to binary prediction, and so I have my prediction model output. It's going to be thresholded at t, and for some reason, large values of this output will allow me to believe that the subject has this characteristic of interest. Okay, so for a particular threshold, I can get predictions. This term, confusion matrix, is very ill-termed because there's nothing confusing about it. It's just a two-way cross classification depicting the actual status of an individual. Do they have the characteristic or do they not? And comparing it to what you predicted for them. Okay? So for a particular threshold, these numbers in the rows could change. However, the column margins will not change. Okay? For a collection of subjects, there are going to be so many with the characteristic and so many without. As you change your prediction model, you may predict 100 as having the characteristic. With one model, another model may predict 200. Okay? So it's going to be important that you keep that in mind, that these these row margins are actually going to be random variables. And what we're representing in this table, the insides are random variables. Okay. So for a particular threshold, I can then look at the accuracy rate. So I'm wanting everything to be on the main diagonal. And I could focus on accuracy rates among the positives and accuracy rates among the negatives. Okay. And then the overall accuracy rate, that's just a weighted average of the two class-specific accuracy rates. Okay. The receiver operating characteristic curve, the ROC curve, acknowledges that these criteria change as you change the threshold, and so it's going to consider changing the value of the threshold, and we're going to see functions plotted for the accuracy rates within each of the classes. Okay? So we would like accuracy rates for plus and accuracy rates for minus to be 1. It just so happens that the ROC curve doesn't plot accuracy minus, it plots 1 minus accuracy minus. Okay? And it's doing this for changing values of t. Why? We really don't want to commit very early to a particular value of t because it's not so clear what value of t is the best. Okay? All right. So the ROC curve, great. Everyone okay? I'm a real strong teacher at heart, so I'm looking for confirmation that you're with me. Okay, so why am I here then proposing to talk about other things? Well, the accuracy alone does not capture everything, okay? So here are two scenarios. Here I have 100 pluses, 100 minuses. This is considered a balanced scenario. On the other hand, here I have 100 pluses and 1,000 minuses. So the minuses are 10 times more prevalent than the pluses, okay? In this scenario, my prediction model has done a great job. It has led me to overall accuracy of 90%, class-specific accuracy of 90%, and the same here, okay? Now let me remind you of those examples that I originally talked about. Let's talk about the bank example. The bank is trying to decide who to grant a loan to, okay? And their prediction model here says that, well, these 100 people, we're predicting that they will pay off their loan. 90 people eventually do pay off their loan, 10 default. That's not so bad. Here, this model is saying 190 people will pay off their loan, 90 people pay off their loan, 100 people default. Okay? Accuracy says both of these models are equally effective. Do you agree? Okay. And it depends on what it is you want to be focusing on. If you are coming from the point of view of the bank, you might be losing your job, okay? Because a 47% rate is not very desirable, okay? And so the question really becomes, what is your interest, all right? And if what you really want to be doing is to say among the ones that are predicted to have this class, you want to actually find a large percentage, then that's what you ought to be focusing on. And there is a measure for that. It's called the positive predictive value. And if you look at it, it's that 47%. Okay, this balance scenario had a 90%, and there is a corresponding measure that says among the things predicted as missing that class. So here you would predict that 910 individuals would default. 900 of them actually defaulted. Does the bank really care about that? Well, no, not really. Okay, the bank is not interested in monitoring people who are going to default per se when they're trying to make a decision of who to offer a loan to. The interest is in one class, okay? And so I'd like to skew your attention to this, this scenario. We're interested in one class. And although this measure is interesting, I really don't need to keep track of it. Although the accuracy rate among the negatives, that's interesting, I really am not interested in long-term tracking that. And the starred characteristics are what I'm interested in, okay? If that's what you need to be doing, then you need to be looking at the precision recall curve. Okay? The precision recall curve plots this, and it plots this. And this F measure is a combination of those two measures, just as the overall accuracy is a combination of accuracy plus and accuracy minus. And the F measure, I'll show you the equation in just a little bit, it takes values between 0 and 1, 1 meaning perfect performance. Okay? So you can see here that the F measure pointed to this scenario as very good, whereas it pointed to this scenario as needing possibly some improvement. Okay? All right, so now here is the PR curve, the precision recall curve. It is going to allow this threshold T to change, and it's going to plot accuracy rate among the positive class, just as the ROC curve did. But there's a slight difference. The ROC curve plots accuracy plus on the vertical axis, whereas the PR curve does it on the horizontal axis, and the names are different. So the precision recall curve was introduced in the artificial intelligence literature, and they just had different names, okay? And I think that's part of the difficulty of this thing catching on in the statistical and mathematical literature, because there are all these different names. So statisticians called accuracy plus true positive rate or sensitivity. Data miners, artificial intelligence folks call it recall. Okay. What statisticians call positive predictive value, artificial intelligence folks call it precision. Okay. Before I go on, I'd also like to point to this bullet here. What is so an ROC curve will look typically like that, okay? And the goal is to get the ROC curve to get to this point right here where this would be 0 and this is 1. This is your ideal location, okay? It's never going to get there in practice. And so the idea is just to keep pushing it up, and a measure of how close it gets is the area under the curve. Okay. So the larger the area under the curve, the better the assessment. And again, this is because you are not yet willing to choose a particular threshold. If you're willing to choose a particular threshold, there is no need to consider the entire curve. Okay. So this area under the curve is the common approach to summarizing an entire ROC curve. So now I'd like to show you two curves from a real data set. Okay? And these are from two different models fit to this data set. The blue curve is from a logistic regression model, the red curve from a random forest model. And the question is whether there is great separation between these two models. And the answer is not huge separation. You can see that very early on, these two curves cross each other several times. And it seems as if there is not much, I mean, they look virtually identical. So with this graphic, you're drawn to this separation. And with this separation, the conclusion would be that the logistic regression predictive model was more effective. Okay? The question, though, is who in their right mind would live with a false positive rate of 40%, which is where this big gap seems to be happening? Where would you want to be? You'd want to be here. Okay? The precision recall curve, on the other hand, gives you this. And it shows you very clearly that there is separation. It shows you that for recall values, so in the PR curve, the place you want to be is here. Recall should be 1, precision should be 1. Okay? So neither of these curves does well. Okay? But when you are having great precision, your recall is lousy. And the longer you proceed, your recall is just getting worse. What does that make any sense? Well, if you're having a predictive model, your first few predictions are likely to be your best, right? You can get the first few, and after a while you start dropping off. Well, your first few will give you a high precision. So precision, let me remind you, says you predict something to be active, You test it, and it actually is active. Okay? Recall is trying to capture, there are 100 actives. How many have you gotten? Okay? Well, when you are getting this perfect precision, you have not seen very much of the data. Okay? So it's important to know the properties of these curves as you try to interpret them. And this curve is used, and it's actually only a very recent proposal, but it has been used, and people will look at the area under the curve to assess whether a model is effective or not. If you compare areas under the curve, you get an opposite decision. You get here that the random forest model is better. Okay? So now I'd like to talk about, well, first, okay, so let me do a little bit of summary. Why the PR curve? There is, yes.
Question on the previous slide.
Sure.
So you're seeing large values of T at the left side of this? I mean, as I understand, these are different points on the two curves represent different values, different threshold values.
Yes, so the thresholds are not necessarily lined up. That's correct. And these are...
Thresholds are on the left, from what you said. Is that right?
The larger thresholds will result in you predicting fewer things to be active, yes. So at the very beginning of this curve, your threshold is the largest. Yes. Yes.
So why does the blue curve start increasing in the beginning?
So this is in theory, that should not happen. So what actually happens is that at your highest threshold, what you think ought to be a really good prediction, you test it and it is not. Okay. So you start lower than you expect. Anything else? Okay. So I think this is a very, it's not technical, but it really is important that you look at the graph and the graph points you to the important relevant areas. So what do I mean by it's zoomed in on the region for small false positive? Here, we are interested in a small false positive rate, but you really can't see any separation. That's just the way the graphic is limited. Whereas the precision recall curve, it allows you to see that separation in that small region. Okay, and notice here, let me just go back. Small FPR corresponds to small true positive rate. Okay, so here you really are seeing this sort of separation is corresponding to small FPR. It's where you want to be. So just the perception is, I think, important, but more important is this difference between utility and discrimination, at least the words that I choose to use. Discrimination would be, Du Bois was interested in discrimination. Parkinson's disease versus not Parkinson's disease. It is equally important to identify both of these, okay? In drug discovery, when we have millions of compounds available that need to be tested, we don't care about finding junk. We care about finding the 0.5% that are actually active, okay? So for that case, we're not interested in discrimination. We are interested in discrimination only to identify the positives, okay? We also are interested in utility. We have our prediction, and we want to know, can we rely on that prediction yielding us positives? Okay. Okay, with that behind us, let me show you this F measure. It's not a simple arithmetic average of the precision and recall. It's this weighted harmonic mean. There are and if you've worked with harmonic means, I would love to talk with you because some of this is not very intuitive to me as to how, why this works. as well as it does. But here there are two popular representations, and really it's just a matter of reparameterizing, okay? And you can allow the weight to increase on the recall or the precision, okay? Well, I'm gonna keep on going, okay? Our focus is comparing the ROC curve and the PR curve. There's a lot known about the ROC curve. Decades of work is available. Can we transfer that work to the PR curve? These two spaces, there is a very strong duality. As you can probably guess, when we think back to this confusion matrix, this one here, we're talking about 4 numbers, okay? And if you focus on these two, you have the ROC curve. Well, if you focus on another 2, you have the PR curve. There is a strong link between these two spaces. So we should be able to learn a lot from what we know about the ROC curve. And the biggest difference, though, is that the ROC curve is not affected by the prevalence. It's not affected according to whether you have balance or imbalance among your classes. Okay? In fact, that's seen as a positive property of the ROC curve, that it is completely blind to your prevalence, whereas the PR curve is definitely affected by prevalence. Okay? And the issues with trying to take everything you know from the ROC space and use it in the PR space is that you may get misleading conclusions. So there is this one-to-one relationship, absolutely, and point estimation methods work in general. I'll show you some evidence of that. However, when it comes to looking at the area under the curve, so what folks do is under the ROC curve, they'll get a number, and 0.98 is going to be considered really great. And you might keep that number of 0.98 as a reference for different applications, different data sets. Well, the PR curve, you can't do that. If you are comparing that area under the curve for a particular data set, that's fine, but across data sets, it won't work. And when it comes to confidence bands, so you're going to be estimating PR curves, and you would like to bound the range of what you might expect for your PR curve. The things that you can do with the ROC curve do not work. They're disastrous with the PR curve. Okay? So that's where my work comes in. So I want to help you understand, 30 minutes left? Okay, great. I want to help you understand what you should expect for these curves. And so a little more notation. D is the status, the truth, okay? The D comes from the ROC literature. ROC was developed in biomedical applications, and D usually stands for disease status, okay? Alpha is the prevalence rate, what proportion of diseased individuals we have, and I'm interested in cases where alpha is relatively small. The output from the classifier, this F hat X, for now I'm just going to call it Y. Okay? Typically it's some estimated probability that a particular subject is diseased. Okay? Now, to actually get a prediction, I apply the threshold T. And what I want to be focused on is what's happening to the score given disease status. Okay? So I am viewing this as having a probability. Why? Well, it's based on, eventually we're going to be using data to guide all of this, and there's randomness. Okay? What we want for these distributions is separation. If the scores for the diseased individuals or the people who will pay off their loan do not differ in a meaningful way from the scores for the people who will pay off their loan, then this problem is hopeless. Okay? Your method, your prediction model simply doesn't work. So what we want, even more specifically, is that this distribution should be stochastically larger. Okay? So these graphics represent some scenarios of stochastic largeness. The dashed curve represents the probability distribution for the junk. Let's call them junk, okay? The solid represents the probability distribution for the actives, okay? So we've seen here that the actives have larger scores in general compared to the junk. Similarly here, okay? With that information in hand, TPR is another way of saying ACC plus. We can obtain it just as 1 minus this CDF. FPR is 1 minus this other CDF. And you go through these steps and you get very quickly that the ROC curve has this closed form, very tractable expression. Okay? So why is this even necessary? The ROC curve, I said, at different thresholds you get different points, but it's not really a function of threshold. The horizontal axis is not the threshold. The horizontal axis is the false positive rate. Okay, so this work is just to re-express it as a function of the false positive rate. The reason that this expression is useful is that you can get some nice clear properties. For example, an uninformative classifier will not separate the two distributions. The active class and the junk class will have the same CDF. You see that if you put the same CDF in here, you get some cancellation, and the ROC curve is just this line. Maybe I should draw another version without all the shaded. It's that line, okay? So relative to this y equals x line, how much further can you get? Okay? There are some other nice properties of the ROC curve. It's going to start at 0. It's going to go to 1. It can occur anywhere in this unit square. It's non-decreasing. If you're lucky, it might even be concave, okay? But it's certainly non-decreasing. The PR curve, on the other hand, which can be expressed in a nice closed form expression, let's think about what happens if we have uninformative classifiers, okay? Which means, again, that these two CDFs are the same. Now the PR curve takes the constant value alpha. Okay? So this is not the scenario. The baseline is alpha. Okay? Furthermore, the PR curve starts at 1, and it goes to this number. So what is this Q? It depends on the support space for these two distributions. And very often, and for the examples I'll show later, this Q turns out to be 1. And so really what is happening is you start off at 1, typically, and you go to alpha. Okay? However, there is no guarantee that you're going to have a monotone function. The function is only non-increasing if this condition holds. Okay? So it depends on the probability distribution functions within each of the classes. Okay? All right. So let's see some scenarios, and I'm not sure how much of this you can see. So in this case, the area under the ROC curve is 0.96. That is considered large, pretty large. This is considered great separation between the scoring values for the two classes, okay? The ROC curve is here. You can hardly see it because it's so close to this vertical axis. The line of reference is this diagonal line. Can you see it in the back? Yeah, okay, great. Okay, what's happening with the PR curve? Well, the PR curve here, there's that one and that one and that one and that one. Why do I have 4? It's because I consider 4 different prevalence values. And it changes according to what the prevalence is, okay? As you can see, there's the prevalence, okay? So if the prevalence is 0.1, then the curve takes this form. Its reference value is this horizontal value at 0.1. And then there's this other curve here. Well, what does it represent? The PR curve cannot go below that value. The ROC curve can be anywhere in here. Okay? The PR curve has a lower bound. Right? So as you think about its distributional properties, this lower bound creates some complications for it, right? So here, this is the scenario of balance. The prevalence here, I know you can't read that text, is 0.5. So the PR curve ends at 0.5. The lower bound is this. So the PR curve cannot exist in here. Would it make sense to report an area under the PR curve going from here all the way there, knowing that this region is not accessible? Okay. Furthermore, you know that the boundary is alpha, and it's going to change according to your data set. Okay? So one of the recommendations I make later is that this alpha needs to be accounted for. Here's another slightly different scenario where we are still looking at strong separation, but this distribution within the positive class is no longer looking like a nice normal. Okay? However, we see a lot of the same patterns as we saw in the previous graph. Here is a scenario of moderate separation. Okay? So here we have both classes having normal looking distributions, and the only difference is the difference in mean. This is considered as moderate separation. Area under the ROC curve is 0.76, and the shape for the PR curve is just quite different from what we saw before. Let's get to some more interesting things. What happens if you have strong separation but you have reverse? Okay, so remember we are thinking about applying a threshold. Let's say the threshold is 0.5, and anything that's above anything that has value above the threshold is declared to be active, anything below as junk. Well, this is actually the active class. This would be a problem. And that happens sometimes. All you do is relabel. Okay? So you have to be mindful of what side are you going to choose, large values of your score or small values. For the rest of the talk, I'm going to not think about this reversal and give you now a little bit about the data set that gave us the previous PR and ROC curves. This data set has been beaten to death in drug discovery. Monoamine oxidase inhibitors, they were used for a while to treat depression until it was found that they created some toxicity. Okay, do you want to be toxic or depressed. It's a tough choice, okay? So they stopped treatment, but this data set, you know, in the pharmaceutical industry, data isn't shared. So the fact that this was shared was fantastic. This assay had a response value, a response variable that could take 4 categories. 0, these were junk, okay? But categories 1, 2, and 3, these represent different levels of activity. And potency level 3, there's been lots written in the literature about what's going on with those compounds, okay? Everybody is basically able to identify those compounds. You know, you build a halfway decent predictive model, you can get those. These 2 classes are not so much, very hard to find. And I'm telling you that because it's relevant for what's coming later. So for this presentation, I labeled the 0 as the junk, and I combined potency levels 1, 2, and 3, all of that into one active class. And so my prevalence is 0.17. This is actually much larger than we typically see in drug discovery, much, okay? The methods that were run, just a simple logistic regression. I made it easy. I eliminated some predictor variables, and random forest can easily handle more predictor variables, so I allowed it to work. It does better with more predictor variables. And the score, the result from these predictive models, is the estimate that a compound is active. Okay? And for everything that you're about to see, I was careful to build a model using some data and evaluate it using left out data. The procedure was 5-fold cross-validation. Okay? So what happened? Let's look on this side for a minute. Here, let's look in this column. This is for the logistic regression fit. These are histograms, in this case, of the predicted score. Okay, so the output from my predictive model up here for the junk. Okay. This is the histogram of the output from the predictive model for the active, the truly active. Okay? And what we're seeing here is this bimodality. Anybody care to tell me what's going on here? Okay, so remember I said these things were hard to identify? Okay, that's what we're seeing here. Okay, the scores, we would love to see the active compounds have larger scores, and we're seeing some of them with larger scores, but we're seeing others with the same score values as the junk. Okay? Those are the hard classes to separate, right? And if we're talking about estimating these, the distributions that go with these classes, for this group, the estimate, spline estimate is here. And for this other group, the spline estimate seems to be this mixture distribution. Okay. It's a similar scenario for the random forest model, except it seems to be a little more spread out in the active class. Okay? And these models led to these graphs that we've already talked about. Okay? So how are these estimates done? These are the empirical estimates, and for saving a little bit of time, let me just quickly say that the estimate here for the CDF is done using the usual step function. Okay? And those step functions are then inserted into the expression for the ROC curve and for the PR curve. Okay? That's one option. What if we had a better way of getting at either this curve or getting directly to this expression? So I'm going to tell you about a very common assumption to improve the estimation for the ROC curve, right? And this assumption is very often criticized, but it's amazingly useful. So all models are wrong, some models are useful, okay? Here, this binormal assumption says that both of the class scores come from normal distributions. Okay? Now, if you are looking here, you're not believing that, right? This is not normal, neither is this, and even the junk class has significant right skew. Okay? However, bear with me a minute. If you can stomach that assumption, then you get beautiful closed form expressions for the ROC and PR, and even more importantly, you get this nice closed form expression for the area under the curve for the ROC. Okay? And with that information, a lot has been done to look at properties, statistical properties for the ROC curve. Okay? So what happens if these assumptions aren't realistic? In fact, people have found that if you can transform to normality, okay, it might not be originally normal, you can transform to normality, it will be okay. And they found that, well, if there's multimodality, which we do have in our data, or if there's imbalance, which we do have, so we have both of these issues, then the usual assumption of this binormal model is very flaky. However, there's an adjustment that is effective at addressing these issues. It is called the semi-parametric estimation. So it doesn't really assume that you have normality. It instead assumes that the expressions are of this form. Okay. With that said, you can estimate these curves, and let me walk you through a little bit slowly. So the solid, those were the empirical estimates. The dotted, those are the semi-parametric estimates. The dashed, those are the parametric estimates that have been recognized to not do well if there's either multimodality, which we have, or imbalance, which we have, okay? So the demonstration here for the ROC curve is that these don't work. The semi-parametric binormal seem reasonable, okay? So from that perspective, can you then transfer that information to the PR curve? Well, the parametric binormal clearly is not reasonable. The semi-parametric is not great. I mean, it's not great, but it's better. Okay? So as we think about how you can estimate these curves and can you get reasonable estimates, it seems as if what we know in the ROC space will transfer to the PR space. And when we use that semi-parametric binormal estimation, our conclusions are completely opposite depending on which curve we are willing to look at. Okay? So now you should be asking yourselves, though, the area under the curve, ROC curves differ in this way, and this difference is smaller. Are we seeing a significant difference? Have we accounted for uncertainty in this data? And at this point, we haven't, right? So how exactly do you account for uncertainty? I am going to, and before I go to uncertainty, I mentioned before that prevalence is affecting your PR curve. And so really, you shouldn't get credit for some of the area under the curve. And the rescaled measure that I recommend is this. Now, you won't have alpha, you'll be estimating it. So you'll be inserting more uncertainty in this rescaled version. But if you don't rescale, you absolutely cannot compare across data sets. And the reason I mention that, in case you're wondering why would anybody want to compare across data sets, for example, data mining is major. And there are very large efforts to look at lots of data sets and summarize which methods seem to do well and be able to walk away and give a recommendation that method ABC seemed to do well on this class of problems, having compared lots of data sets in this class of problems. And so that's why I keep harping on it. I've seen it in papers comparing area under the PR curve where there are different data sets with very different prevalences. It's just not fair. Okay, so how do we account for uncertainty? Well, not very well. The ROC curve, it doesn't do really well when it comes to confidence bands. And the PR curve is exquisitely bad. So what do I mean here? So the true ROC curve, let's say we don't know, but we estimate our ROC curve to be this, okay? Because we use data, we're going to provide some range of ROC curves. Let's say our boundaries look something like that, and we say our ROC curve will be somewhere in here. We do a similar thing for the PR curve. Okay. The question then is, can you make any sort of probabilistic statement were I to repeatedly get these confidence bands about the true ROC curve being found in here? Okay. Can you provide for me a probability that under repeated sampling, my confidence bands will capture the true curve? Okay. That's the coverage probability. And if we claim that these are 95% bands, we would want a probability of about 0.95 of capturing this truth. Okay? Okay, so with that said, I'm going to show you what happens. So this is for the ROC curve. If, this horizontal reference line is at 0.95. What is being plotted on the vertical axis is the coverage probability, and I want it to be 0.95 with this discussion of what the 95% confidence band means. Okay? And I'm doing it pointwise. So each point on the horizontal axis, I'm considering the coverage probability. The method here that's red is the parametric binormal. And the scenario, the simulation scenario, fits parametric binormal. Okay? So I have not set up the method to fail. I'm trying to help it here. Okay? So parametric binormal is reasonable. The coverage probability here is actually quite conservative. It's greater than 0.95. Awesome. These other methods, so here this is the empirical estimate. It's not doing so well. Okay. This is the semi-parametric, which is, and maybe you guys can correct me, it is a very, very popular way to estimate the ROC curve. It's the way that fit our data better. Okay? But it is horrible. This is the PR curve. Everything is just bad. Okay? For another scenario where the binormal model does not fit, the confidence coverage, the coverage probabilities are just, this is just horrendous. Okay. And what's going on? It's because the positive predictive value, our denominator is random. In addition to the numerator being random, the denominator is random. So I'm going to take you back way to the beginning. And I want to point this thing here. For the ROC curves, the numerators, n plus and n minus, those are fixed for any given data set. But for the positive predictive value, this denominator is random, and it increases the complexity of the distribution. Okay? So I am now going to summarize and sort of remind you, so my talk has been a little bit schizophrenic. At the beginning, I encouraged you that the precision recall curve needs to be considered. There are scenarios where it is the right thing to do. And then I went into, there may be some problems using it, okay? So, I encourage you to use it. Estimation is great. There are lots of R packages. If there's imbalance, use the PR curve. There's lots of software, for example, in R, freely available. But when it comes to using uncertainty, I recommend bootstrap methods. Okay, those are the only reliable. I mean, that's the best thing that it seems reasonable to use these days. Okay. And there are, I'd like to acknowledge a former PhD student at George Mason. And here are resources that I found very useful. So ROC curves, that has not been part of, I've done spatial modeling, I've done design of experiments, I've done prediction. ROC curves have been new for me. So this is a new direction, and I've totally enjoyed it. And I thank you for your attention. I would welcome questions.